So we have seen how to explore connectivity using breadth first search. So now let's look at the other strategy which is commonly used called depth first search. So in depth first search, instead of exploring all vertices level by level, each time we explore a new vertex, we immediately explore its neighbors. So we start from a vertex I and visit the first neighbor j from I which is not yet explored. Then we suspend the exploration of I and explore j instead. And you keep doing this until you can go no further. So when you get stuck, when there's nothing new to explore, you walk back because you have already left some vertices earlier unexplored because you suspended. So you go back to the nearest suspended vertex that still has an unexplored neighbor, and then you explore the next unexplored neighbor of that vertex. So the way to think about it is that all the vertices which are pending, which are suspended, are now in a stack. So you build up the stack as you go deeper and deeper into the graph. And then whenever you get stuck at a dead end, you walk back up and you process things earlier in the stack. So as before, let's execute this algorithm by hand on our graph and see how it works before we write the pseudocode. So this time we are starting at 4. So the first step is to mark 4 as visited. So we start mark 4 as visited and we identify that it has 3 neighbors, 4 neighbors, 1, 3, 5 and 6. So taking them in order, we start with 1. 1 is not visited, so we mark it as visited and we put 4 on the stack, saying we are suspending the execution of 4 because now we are going to explore 1 instead. So now we go to 1 and then we see that 1 has neighbors 2, 3 and 4. Among these the first is 2, so we put 2 on the stack since it was not visited. We mark 2 as visited since it was not visited earlier, and we put 1 on the stack saying now we are suspending 1. So now we look at the neighbors of 2. So neighbors of 2 are 1 and 3. 1 has already been visited but 3 has not. So we will now mark 3 as visited and suspend 2. Now when we come to 3, it has 2 neighbors, 1 and 2, but both of them are already visited, so there's nothing to be done. So we must go and we must go back to the last vertex which we suspended, namely 2, and explore its neighbors. So we go back to 2. So we had already declared that 1 was not to be done. We have already processed 3, so we have to look at 4, but 4 is also already visited, so we are done with 2. So now we must go back and restore the next vertex on the stack which was left undone. So that was 1. So now we go back to 1, okay, and we find that from 1 we had already visited 2, 3 which we had not visited from 1 was visited via 2, so it's already marked, so this is done. And 4 also is where we came from to 1, so this is done. So 1 is also useless. So now we go back to the first vertex we started with 4 and see if there's something more to be done. So having come back to 4, we find that it has more neighbors. We only explored 1 the first time. Right? So now we continue and we find that there are still 5, 6 and 8. Okay? So we pick up 5 and see it's not visited. So we mark 5 as visited and again suspend 4. So from 5 now we have 4, 6 and 7. So we will now pick up 6 and suspend 5. From 6 we have 7, 5, 7 and 8. So 5 is already done but 7 is not done. So we'll pick up 7 and suspend 6. Now from 7 we find that it has neighbors 5 and 6, both of which are already marked. So 7 is a dead end. So we come back and look at 6 again and see if there's anything new to be done. There is an 8. So now we add 8 and again suspend 6. So now we are at 8 and now we have to ask what can be explored from 8. From 8, 4 is already done. It has 4, 6 and 9. Right? So 4 is already done, 6 is already done, but 9 is new. So we add 9 and suspend 8. Then we move to 9. So from 9 we find it has a new neighbor 10. So we add 10 and then we are done because 10 has nothing to do. So we go back and process 9. 9 has no more new things to say because 9, the other neighbors are 6 and 8 which are already done. So we go back to 8. 8 has nothing more to say, so we go back to 6. 6 has nothing more to say, so we go back to 5. 5 has nothing more to say, so we go back to 4. Now when we started this whole exploration, we did it by 4 to 5. Now we look and see that 4 to 6 is already done. Sorry, not 4 to 6, 4 to 8 is already done. So there's nothing more we can do from 4. And so this exploration is done. Okay. So what we did explicitly with a stack can be done more cleverly if we just implement it recursively. So whenever we visit a new vertex j, we call DFS of j and suspend DFS of the current vertex I. So we don't have to explicitly maintain the stack that we were simulating, because it will be implicitly maintained by the recursive function calls. So DFS is therefore a very simple algorithm to implement. So initially we say for every vertex visited is 0. And remember, like in BFS, breadth first search, we want to keep track of where we came from. So we will say that everything has an undefined parent. Now we initialize, we call DFS of the start vertex. So when we call DFS from a vertex, we mark it as being visited. Right? So the first thing we do is to mark it as being visited. And now for every other vertex that it is connected to, we do the usual thing. We check whether or not that vertex is already visited. If it is not visited, we want to visit it. So how do we visit it? Well, we mark its parent as being I, and then we suspend this DFS and call that DFS. So this is what we were doing explicitly with the stack, but it's much easier to do recursively. So DFS is a very, very simple recursive algorithm. It starts an I, look at every unexplored neighbor, and recursively invoke DFS on that unexplored neighbor. So what is the complexity of depth first search? Well, each vertex is marked and explored exactly once. So we do DFS of j once for every j. So these are order n calls. There are actually exactly n calls if everything is reachable. Now when we call DFS of j for a particular j, we need to examine all the neighbors of j. As we saw before, if we have an adjacency matrix, that means we have to look at the row j and we have to look at every entry in this row. So this takes order n time. So we have order n calls, and each call takes order n time. So overall we have order n squared time. On the other hand, if we use an adjacency list, then when we look at the neighbors of j, we only have to look at the exact vertices it's connected to. And as we said before, if we count across all the calls, each edge will be accounted for twice, once from I to j and once from j to I. So the total number of calls, the total number of steps to scan the neighbors will be order of the number of edges. So the overall time will be linear, m plus n, like breadth first search. So both depth first search and breadth first search are linear in the size of the input if we use adjacency lists. So one big difference between depth first search and breadth first search is that the paths that breadth first search discovers are not shortest paths. Right? So if we have a graph, as we saw before, a triangle like this, where we have 1, 2, and 3, then what depth first search will do is it will find a path from 1 to 3 which goes via 2 if we take the smallest neighbor each time to explore. So when I actually come to the 1, 3 path, I will find that 3 is already visited and I won't mark it. Right? So it appears therefore the depth first search may not be doing something very useful. But actually this recursive way of exploring gives us a lot of information. So many useful features about the graph can actually be extracted by recording the order in which DFS visits vertices. So for this, we augment DFS with something called numbering. So we maintain a counter which we increment every time we enter a vertex when DFS starts on a vertex and when it leaves. So we associate with each vertex in the graph two values. The value of the counter that was there when I did DFS of j for the first time, and the value of the counter when DFS of j exited. So this is how we would do this in our algorithm. So we start by initializing this counter to 0. Right? Now whenever I invoke DFS of I, the first thing I do is assign the current counter value to something called the pre-number of I. Okay? So this is the number of the counter before the DFS of I actually started, and then I increment the counter. Likewise, when I'm about to exit, I mark post of I equal to count, and again I increment the counter. So this says that so in between, remember, a lot of recursive call happens. So this count at this point is not going to be the same as the count which I incremented. There's going to be a lot of stuff happening in between, and it turns out the order in which these two numbers pre-I and post-I fill across vertices, I can actually recover a lot of information. Okay, so let's look at this example that we did before. So supposing as before we start at 4. Okay, So we'll say that its pre-number is say 0 because we start there and then we increment and then we go to 1. So when we enter 1, the count is 1. So its pre-number is 1. And then we go to 2. Its pre-number is 2. Then we go to 3 and its pre-number is 3. And then we immediately leave 3 because we don't have any new neighbors to exit. So its post number is now 4. So I'm writing the pre-number above and the post number below. Then I come back to 2 and I find that there's nothing more to be done at 2. So I exit from 2. So its post number becomes 5. So notice that here I entered at step 2 and I left at step 5. And in between I did 3 and 4 somewhere else. Likewise, I come back to 1 and I find that it has nothing new to say. So now I leave 1 at step 6. Then I come back to 4, but I'm not finished with 4 because I can do 5. So I enter 5 at step 7. From 5, I enter 6 at step 8. From 6, I enter 7 at step 9. Now from 7, I can't go anywhere else. So I leave 7 and I come back to 6. Okay. Then from 6, I look further and I find 8. So I enter 8. I was at 10 at that point. So now I enter 8 at step 11. From 8, I enter 9 at step 12. From 9, I enter step 10 at step 13. Then I leave 10. I leave 9 at 15. I leave 8 at 16. I leave 7 at 17. I leave 5 at 18. And I come back to 4 and I finally finish at 19. Right? So I have with each node now these two values, a pre-value and a post value. Right? So I have a pre-value and a post value. And it turns out that this pre and post value can be very helpful. Okay? So we can find out things like whether a graph has a cycle. So this is a cycle, right? So whether a graph has a loop like this. Or we can find out whether there are vertices like this. So this is a special vertex because if I remove this 4 from the graph, and the graph which was earlier connected, everything could reach everything, is no longer connected because there's no way now to get from 1 to 3 to this lower segment. Okay. So are there such cut vertices? So these are various things that can be computed using these DFS numbers. We will see some of these computations in later lectures, but this makes DFS actually a much more useful exploration strategy than breadth first search. So BFS does give us shortest paths, but on the other hand, DFS gives us a wealth of information which is implicitly hidden in this recursive order of exploration, which we can exploit to find out various structural properties of the graph for free, more or less. While we are doing DFS, we can find out many interesting things about the graph.